This is Joe Straathoff's ENME 351 Lab 4 Sampling and Aliasing. Over here is my girlfriend's cat, and her ears will show up later on in the presentation. So for our Arduino code, we declare the pot and the scope pins, we start our serial output, and we set the pin modes. And then in the loop, we have an unsigned long that is the timer in microseconds. That's when the loop starts. And we read the potentiometer and we read the oscilloscope pins. Then we calculate the frequency. I divide by 1017 because I calculated 1017 to be the reading when the pot is maxed out. So that way we can get a frequency of 500 hertz. If I divided by 1023, it wouldn't quite make it to 500. You get to like 499. Then we print out the scope reading for processing to deal with. And then we set our new time, which is the end time, to be the timer plus 1 million, which is 1 million microseconds in a second, divided by the frequency, which is 1 over the frequency is the period. So that's the timer plus the period in microseconds. And we just have a while loop that will wait for that period of time to pass before starting over again. So this is with an input signal of 75 hertz. And with a sampling rate of 100 hertz, we see that we have aliasing because we would expect a 75 hertz peak, but we get one at like 25 instead. Same thing with 142. We don't quite get it at 75. It's more like 66. And with 200 and 500 hertz, we get the expected output. So there's no aliasing there. With 100 hertz, so with a 100 hertz input, we have aliasing on the 100 hertz. You have like half a hertz is the reading, which is not 100 hertz. Same thing with 142 hertz. We get a reading around 42, which is, again, not expected. With 200 hertz, we get a reading at like 99, which is close enough. And same thing with 500 hertz is we get a peak at 100, which is what we would have expected. Now at 215 hertz, we have aliasing on 100 hertz, 142, and 200. The 100 hertz gives us a reading around like 14. 142 hertz has a reading around like 68. And then 200 hertz gives us a reading around like 24. And the 500 hertz has a reading at 215, which is what we expect. And now at 300 hertz, we alias on all the frequencies. We have 1 hertz on 100 hertz, kind of like 17 on 142. 100 hertz on the 200 hertz, and then looks like 200-ish on the 500 hertz. So now the folding diagram example, we're going to look at an input frequency of 215 and a sample rate of 142 hertz. So to find the Nyquist frequency, we divide our sample rate by 2, and that's 71. To find the n value, we divide the input frequency by the Nyquist, which gives us 3.028. Then we follow our folding diagram up to 3.028 and fall all the way back down, which is at 0.972, and 0.972 FN is 69 hertz. So now this is the entire chart. We have our Nyquist frequencies up top, 250 hertz, 100 hertz, 71, and 50, and then the theoretical frequencies, and we can see that the 500 hertz only starts to alias at 300 and so on. Most of the values are pretty close between experimental and theoretical. The only one that's different is right here, 200 hertz sampling rate at 215 hertz input, and that don't quite know why that happened. Now to demo the triangle and the square. Escape, close this. So I am inputting a square wave into our system, and we can see that we have multiple successive peaks that get shallower over time, and this makes sense because we are essentially creating a Fourier transform for a square wave. Now if I change this to a triangle wave and move my 2 little leads over. So we have a triangle wave, and we again have the Fourier transform of a triangle wave.